Today we're going to be talking about two new types of prediction methods. One is called k-nearest neighbors, and the other is called logistic regression. So k-nearest neighbors is just another way that we can predict outcomes. And the idea is that we want to predict a new data point by looking at the k other data points that are closest to this one. So that's why it's called the nearest neighbor. If that outcome is a number, so in salary, then we just take the average of whatever those data points are. But it also lets us do something where what we want to predict is something else, so a binary. So whether or not somebody is a registered voter, 1 or 0, we can actually assign a probability that that person would be a registered voter. So it's kind of a nice algorithm in that respect. Looks a little bit like this. Let's imagine we have data points out here. And we have a new data point here in the middle, and we want to know what are we going to predict for the sales of our new store. So we've got median household income, and we've got population within some certain range, and we want to know what are the sales going to be for this new store. We just look at the 3 closest points that I've circled here, and we take the average of those 3 points, and that's going to give us our prediction for sales for this new point here. And again, we just really need to choose one thing, which is k. So k equals 1 says I'm just going to assume that that my new point is very much like its closest data point. And k equals n, where n is our number of observations, is just going to take the average of our entire data set. Our trade-off is we want data points that are pretty similar, are probably going to be have similar sales, but we don't want to have random noise. So if we have k equal to 1, there's probably going to be a lot of random noise. And if k equals n, then we aren't really dealing with very similar observations. And we'll choose k by doing cross-validation. So we can build the process, try it out for different salaries, and then we can figure out what's going to be our best way to do that. So one thing that we need to do when we're making predictions here is we need to make sure that we normalize properly. So we'll learn a new way of normalizing here in just a sec. So let's jump into RapidMiner here. And in RapidMiner, we're going to build out our data. So we already have our sales data. So we're going to build out this process by importing our sales data. And we're going to do cross-validation on this. We'll leave actually let's take performance here, performance over. And we'll use our local random seed just to make sure you're seeing what I'm seeing, 1, 2, 3, 4, 5. Now, if I double click again on cross-validation, it's going to bring in an option here. So I'm going to look for something called k-nearest neighbors. And I'm going to do my normalization inside of my cross-validation process. So this is going to normalize based on the training data, not on the full data set. So I'm going to bring this in and then bring out my model. When I get to my normalize, remember to change this to a range transformation between 0 and 1. And let's do k-nearest neighbor with k equal to, say, 3 to start. Now, when I do my my testing later, I need to bring in apply model to this twice. So I'll bring in the first apply model. And what that is going to do is it's going to take our testing data and it's going to apply a model to that. And I'll get to what that is in just a second. And then we're going to take in our second apply model. And that's going to take our data here. And it's going to take the k-nearest neighbor model here. And then we'll have performance that we're going to connect to the end. So what we need this first apply model to do is to use the normalization that is used here. And the reason we worry about that is because just because of random selection of data points, even though the training and the test data are sort of drawn from the same distribution to the same observations in the whole, there's going to be small differences between what's the maximum and the minimum in this training data set than there is in the testing data set. So we're going to bring the pre output here, which is a way for us to pass through what this normalization does. Think of it as sort of telling us what the min and the max are for our data set. And it's going to use that, if we do this throughput here to the model here, and then we use our test data to the unlabeled here, then that's going to pass through our data. So what it's going to do is it's going to calculate a normalization based on the training data, run k nearest neighbor with k equal to 3. Then it's going to apply whatever that normalization was to our testing data. Then it's going to calculate the k nearest neighbor, and then it's going to give us our performance metric. So when I hit play here, this will take a little bit sometimes on a large data set. So that's just something to be aware of. It can be pretty big take a lot of time for us to run that. Let's memorize this number. It's about 45,400, and that is, again, with k equal to 3. So we'll try that with k equal to 5, and we get 42,000. So in this case, we actually prefer k equal to 5. So this is our RapidMiner process. Here's the options that I was using. With k equal to 3 and k equal to 5, we get a lower root mean squared error with k equal to 5. So we may also want to change some of the other options that you see in RapidMiner, such as with k nearest neighbor, we have something that's called the weighted vote, and the weighted vote is giving more weight in the average to the closest observation than it is to one that's a little bit farther away. So you may want to change that. In this case, it's not going to make a big difference, either way. So now that we know that k equals 5 is better, let's use k nearest neighbors to predict new salaries. So it's similar to what we have done in linear regression, but we need to adjust that a little bit. Again, we're going to use the pre-output and the apply model operator to make sure that we're using the same normalization. That's not something we had to worry about in linear regression, but it's something we do need to worry about whenever doing something normalizing like this. So you may want to save this process as something like k nearest neighbor cross-validation, whatever you'd like. I'm going to go ahead and just remove it and start a little bit over again. So I'm going to start by bringing in the normalize. I want to normalize our data. Again, remember to make this a range transformation between 0 and 1. And then we're going to bring in k nearest neighbor. So we're going to bring in our salaries, normalize it. We're going to take that, feed it to k nearest neighbor with k equals 5. Then we're going to bring in our new salaries data. In our new salaries data, we're going to apply the same normalization that we had before. So we can take the pre out to mod here and take out here. And then I can do another apply model where I'm going to apply k nearest neighbors to this normalized data and take that out. When I run that, here's what I get. Here's my predictions, and here is my age and years of post-high school education normalized, and the prediction that I'd get for those 10 new salary numbers. And again, that is here with k equals 5, because that's what I found was best in that previous step. The nice thing about this is we can actually do this with a new type of data. So let's get rid of our salaries data and instead bring in what we're going to call the voting data. So if I go to my sandbox, I've got something called voting. This has two different sheets on it. It has data and it has new. In the data sheet, I see people's age and years post-high school education and whether or not they're registered voters. So this is what we're wanting to predict, whether or not they're a registered voter. And then in the new data, we only observe their age and years post-high school education. So let's import the data itself. When you get to this step here, don't forget we want to change this role to be a label here. So we're trying to predict registered voter. And we also want to change the type here to be binomial. So we hit next, finish, and that's going to import my voting data. I already have it there, but I'll go ahead and override it. Then I'm going to import data again, go back to my voting data, and change this from the data sheet to the new sheet. So I'm importing the data that I'd like to predict. There's nothing to change here, so I can just import that as it is. But I do need to make sure that I called this something like voting-new. That way I don't overwrite the voting data that I had. So now I can delete my salaries data, I can delete my salaries new data, and I can bring in my voting data and my voting new data. And with the exact same process, but with just 2 new data sources coming in, I can hit play. So I can now predict voting, whether or not somebody is a registered voter. And that's what this first column here, confidence 1. So this confidence means what is the probability that this value that we're trying to predict takes the value of 1. And we're trying to predict whether or not somebody is a registered voter. So here it's a 17.3% probability that somebody is a registered, that this person with these characteristics is a registered voter. And so we're going to make a prediction of 0, and that's because this confidence 1 is below 0.5. So if we look through, anywhere where that confidence is above 0.5, we're predicting 1. Anywhere where it's below 0.5, we're predicting 0. And then we have this other column here, which is confidence 0, which is just 1 minus the probability, 1 minus confidence 1. So this is the probability that somebody is a registered voter. This is the probability that somebody is not a registered voter. The nice thing about that is k-nearest neighbor, we just flip the data sets. But in other things, other methods, we won't be able to do that. So in linear regression, we will be, if we wanted to predict whether or not somebody is a voter with linear regression, we'd have a problem because linear regression would let us have predictions that are greater than 1 or less than 0. And probabilities that somebody is a voter cannot be more than 100% or less than 0%. So we're going to use something that's called logistic regression, which doesn't let this line go too far or go above 1 or go below 0. So it's going to turn into a little bit of an S curve here. So instead of looking at something like this, it's going to look like this. And that's all logistic regression is sort of changing our prediction from a straight line into a curved line like that. Now just some details on logistic regression. What it actually does is predict the log odds instead of probability. And so that's sort of what it is estimating here. And what we really care about is that it's going to give us some probability of, in this case, voting. And it will define a threshold above which we predict, yes, that person's going to be a voter, or no, it is not. And usually for RapidMiner, the default is 0.5, and for most software, you're going to get something that's in that range. All right, so let's go see how we run this in RapidMiner. Let's get rid of the normalize and get rid of k-nearest neighbor, and we'll get rid of there. So I've got retrieve my voting data, retrieve my new voting data, and apply a model. And then what I need to do is sort of 2 steps here. One is something that's called remap binomials. Let me talk about that in a second. Just bring it in. And the other is an operator called logistic regression. So logistic regression is what's going to actually run our regression here. And remap binomials is a way that we can have RapidMiner tell us, or we can force RapidMiner to know what is a positive and a negative. So what I mean by that is when RapidMiner sees this one variable, registered voter, that's a special attribute, so make sure you change single, registered voter, special attribute. It's going to try and guess what a positive outcome means, meaning we're going to define a probability that somebody is, yes, they are a voter. So that's what a positive value is. I'm going to go ahead and code a negative value and a positive value here. If you don't hard code this, RapidMiner will just guess, and it does its best, but sometimes it gets it wrong, and it can actually mean that you are interpreting coefficients that come out of this model as something completely different. So that's how we would run this model, and we'd get some labeled predictions for this new voting data. And if I want to see the model, I can push that mod on that apply model out. So don't worry about changing any other logistic regression variables or anything like that. Everything should be good to go. So we'll hit run there. And this is what we see. This is the logistic regression table. It's something like a regression output that you would see in in just linear regression, except for these coefficients mean something very different. So if a coefficient is positive, that means that this person is more likely to vote with as that age increases. So here we're seeing a higher increase in, or a 1 unit increase in age increases their probability of voting. That's what we see based on these numbers right here. And same with education. Education seems to be going up. Now, if we wanted to look at what these things actually mean, I'm going to do sort of 2 different calculations for us. One calculation is just converting the odds, the coefficient into an odds ratio, and so the coefficient that we're getting here is 0.091, and that means we have an odds ratio that is just the exponential of that. So what this odds ratio is it tells us how much more likely is somebody to be voting when their age increases. So they go up by 10%, right? So if they were at 50%, they're going up to 55% is basically what it's telling you. The other thing, which I think is more interesting here, is how we get to a vote probability for somebody's given characteristics. So if I jump back to slides here real quick, what RapidMiner is really doing when it does logistic regression is it's predicting something called the log odds. So that's the probability over 1 minus the probability that somebody would be voting. That's the odds, and then the log odds. So the software, when it calculates these probabilities here, this is 0.696. Actually, this 0. Let me see here. Yeah, this one, 0.304. What it's actually doing when it calculates the 0.304 is it is calculating the log odds and then converts it back to probabilities. So what does that look like in Excel? Well, we have our coefficients here. So we have our age coefficient, we have our years of post-high school education coefficient, we have our intercept, and we want to predict somebody's probability of voting based on the new age and new education. So these are going to be inputs. Let's just calculate it for, say, this first row of data. This is somebody that's 30 and 2 years of education. So 30 and 2. And then we have our inputs here, which is our age coefficient. If we come back to our logistic regression, we can copy these 3 and paste them here. So there's just copying over our coefficients that we had before. These 5 here are all now inputs. And I'm going to go ahead and name all of these just to make life a little bit easier on us here. Now in a normal regression, we would have the prediction, and that prediction in logistic regression is predicting the log odds. So predicting the log odds is the intercept plus the age times the new age plus the years of post-high school education times the new education. And we get something like that, so negative 0.826. So this is what is being calculated here. And then the conversion that I'm talking about in these slides, this is what has been calculated, so we need to sort of reverse that. We need to calculate the odds ratio, and then from the odds ratio, we can calculate the probability that somebody votes. So that's the log odds, so we can calculate the odds ratio, and we do that by just using the exponential of the log odds. So that's how we take away the exponential, and again, that is simply a calculation. Cell styles calculation, and then what we really want at the end of the day is our output, which is our probability of voting. So probability of voting is going to be a calculation that does the odds ratio divided by 1 plus the odds ratio. So that's going to be our calculations here, and that's where we get that 30.4% that we are seeing when we look at the prediction here for whether or not this person is a voter, 30.4%. And what you'll see in the rest of the slides today is walking you through a little bit of that. So how would you do this in RapidMiner? What do you do with the remap binomials? What do you do with other options? And what do the results look like? A little bit of information about how we interpret this. P-values, again, have the same meaning. So close to 0 is more significant. And then don't forget to check out what we did in Excel so you can see what we did. Now, the last thing I will say is that we would have been able to run this through cross-validation as well. I'm sort of skipping that step just to keep things simplified for us, but we would want to run this through cross-validation just to get an idea of how good this logistic regression model might be for predicting on new data in the real world.